is complete. All right. So okay, without wasting any time, let's get into discussion about the games or game scenarios that are actually adversarial games. So before I start, any question, any comment from last week, from search algorithms? I think one of Emily. I responded to your messages, okay? But I was gonna mention to the entire class that if you are having any difficulty, if you are having any confusion, anything about homework, get in touch with James, okay? He'll be able to help you, okay, guide you, not basically solve the problem for you, but he will be able to guide you, okay? And I also commented some of the functions like is goal state. I don't know, there are a few more, get successors, something like that. I also commented those in the search file. You can take a look at those, the comments, and then you can just simply use the functions, but please follow the pseudocode that I copied in the slides. Because the pseudocode basically has your entire code, but it's in a human understandable language. You need to take a look at that and just need to understand how to convert that into the code, okay? If you're still having issues, get in touch with James, get in touch with me. If he's non-responsive for a while, just get in touch with me too, and we'll be able to guide you, okay? All right, so last week, basically, we've been talking about the problems where we basically needed to devise a plan, right? The entire plan, we needed to create a tree, and then from the tree, we devised a plan, basically a plan, meaning how can we expand the entire tree that we now have and find out the least cost path, okay, least cost path. Remember path. In all your homework assignments, the three parts, basically you need to, so your functions need to return the path. Like from Pac-Man's current scenario, you need to go north, then need to go west, then need to go east. So you need to just give us the path north, west, east, north, south, east, west, and then you need to post. So you need to return that back. So for the entire basically discussion, we have been talking about the finding out the least cost path or the best possible solution. We call that. If you remember, we had start state, right? We had a successor function, we had set up actions, right? And then we had a terminal state. And then at the end, I mentioned that the solution, even in our family Romania problem, I said that the solution would be go from Arad to Cebu, then Fagaras or Fagaras, and then all the way at the end to Bucharest. That's your solution. So in your homework, and what we have been talking about is that what is the least cost path? All right. So when you get successors, right? Get successor function in Pac-Man scenario, it actually returns two things: XY position, all right, current XY position, and the actual path and the actual state, okay, and what the action that can be taken. So far we've been talking about the games where we have plans, okay, and we would find the best the plan basically because we are in a deterministic scenario where the word is known, all right, but we were talking about just a single Pac-Man or just an individual who is standing in the city of Arad and just going to Bucharest, right? So we were devising that kind of plan. Today, we're going to talk about what Ronald mentioned about a couple of weeks ago. What if we have opponents? We have other, players in the game too. And what if they're either random or they're also smarter? What happens? Such as in Pac-Man, we've been talking about, okay, eat all the dots, right? In Pac-Man scenario, we said that our goal is to eat all the dots by taking the least possible steps. Because we said that every time the Pac-Man makes a move, there is a score of -1. So we need to basically reduce those number of steps where it just moves but doesn't eat anything, or it hits the ghost, right? So our idea was to basically just move, but we didn't talk about what the ghosts might be. Or what if we have more than one Pac-Man, right, in the game? Are they cooperating? Are they, just simply random? Are the ghosts random? Are they, be the opponents? Are they literally after you, try to hit you or try to, finish the game, or they're just moving randomly, right? So we're going to talk about the algorithms that actually solve that problem. Okay, so those are called adversarial games. The idea behind the solution is actually the same. We're still going to work, with the tree search algorithms. Okay, I shouldn't say tree search, graph search, because we have the visited the set, the closed set that actually mentions or keeps track of the visited nodes, and you never visit a node that is visited once, right? So graph search, I would say. The idea is still graph search. All right, we're still going to work with the same thing, but we're going to basically make the game a little more complicated and see how we can make our agent or design the agent that is going to maximize its own utility, but then also keeping that in mind that the game might have opponents, smarter or random. Okay, and we're going to talk about minimax search algorithm that is designed to solve those problems. And we also said that there were quite a few games that were solved several years ago, such as checkers, right? Game of Go. Those are really, really complicated games, really complex games. And by complex, I mean that the tree that we can create because of the number of moves that can be made, the tree can grow extremely, extremely large, like trillions or even gajillions moves, right? Extremely, extremely large. How can we optimize or utilize our minimax search algorithm to make it, in such a way, make it efficient that it doesn't have to search the entire tree. Depth first search, breadth first search, uniform class, greedy search, ASR, they all have to basically look at the entire tree. So for small deterministic problems, they're really good algorithms. But today we're going to talk about a few games, a few scenarios in which the tree can go extremely large, and then we're going to talk about how can we use the same minimax search algorithm, but implement alpha beta pruning to make the game more efficient, so that we don't have to my laptop volume is on. We don't have to traverse the entire tree. All right, so let's just start with the state of the art. Okay, so in week 1, lecture 1, we talked about math.
Oh, I forgot.
Okay, we talked about quite a few games that are actually solved using some. I shouldn't say naive, but like in the initial stages of AI, some of the games were actually solved using these algorithms. The state of the art, like some of these games that I just mentioned, they were initially, even though with the lack of available resources, back in 1950s, starting from 1950s, they were actually solved using minimax search algorithms. And that was the time when the AI was in a really early stage. There were not so many sophisticated algorithms or sophisticated solutions to complex problems, and also there was a lack of computational resources. But even then, we were able to solve some problems, such as checkers. Okay, there was a guy called Marion Tinsley. He was actually the checker champion, world checker champion for about 40 years, for 4 decades. He was a checker champion. So back in 1950s, the computer called, I don't know, Chinook, basically using minimax search algorithm, it ended the championship reign of a guy who was a checker champion for over 40 years. And that was using minimax search algorithm. Okay, back in 1950s, at least about 60 years ago. All right, then comes 1997, the chess game, basically Deep Blue. Some sophisticated algorithm, but based on minimax search algorithm, they design and then some undisclosed basically functions that they implemented. They designed basically this algorithm to beat the world champion Garry Kasparov in a 6-game match. All right, So, how many of you know the game of Go? I think I've asked this question. The game of Go. Game of Go, right? So basically, it's a different game from Interrupter because there are so many different moves at every point. Much more, I think there is about 32,000 moves at every step. So now you can have an idea how grow basically the tree can, how large the tree can grow, right? So in 2016, AlphaGo, it was, I think, by the company DeepMind. It's a British company, but it's acquired by Google. All right. So they designed this out. They designed the algorithm. Later, basically, with much more sophisticated, functionality, they were able to again defeat the human champion. But with the game of Go, the problem is this: the tree can go like extremely large because you see in Go, be the branching factor at each step, how many children nodes that you can expand. It is greater than 300. Greater than 300. If B is greater than 300, there can be, like trillions and trillions of different possible moves in the game of Go. Then you can have an idea how large the tree can go. In normal computers, it will not be possible to store that information. Because if you look at the time and space complexity, it's going to be impossible to do it. But we will also talk about quite a bit about in weeks 5 and 6. Now I should say weeks 5, 6, and 7 because we're one lecture behind, right? In weeks 5 and 6, we're going to talk about Monte Carlo simulations. Monte Carlo simulations, all right, and some other randomized expansion methods that actually the game of Go, the algorithm that was designed behind the game of Go, computer-based game of Go that defeated the world champion. If the trees are extremely large, how is it possible to still go to the leaf nodes and find the solution? So what do we have to do in our game scenario for the trees? We have to get to a node that actually gives us the goal, right? That reaches the goal state, right? That's what our main purpose is. So still, some state of the art. It's the games have been these problems, deterministic problems, have been solved. Super complicated, have already been solved. Now there are many more other functions, or many more sophisticated algorithms that are used to, solve even complex problems. And stay tuned, we're going to solve not only just these deterministic problems, these are extremely simple, very simple. Depth research, breadth research, they are very simple algorithms, which is why we started complex. And in the coming weeks, you will see how basically complicated the scenarios can get and how we can design even much more, sophisticated algorithms to solve problems. So that when you just go, apply for a job, a software engineer or machine engineer or something, machine vision, computer vision, data scientist, jobs like those, you will be asked questions like what we will cover in this class. Okay, so there, and then Python, one of the most famous programming language. So we're going to solve those problems in this class. So we're going to consider this class as not just only going over a bunch of slides, but actually solving real world problems using multiple different algorithms, right? So in Minimax, what we're going to do is, you see, as I said, that we had a plan for BFS, UCS, greedy, and ASR search. We had a plan, and we just had to just expand the tree and find out the least cost loop, right? We just had a plan. But here, what we're going to do is at every step, because we are considering, our opponents as smart, like ghosts, we're thinking like at every step, we say that if I take this step, let's say for Pac-Man scenario, say if the Pac-Man, goes east or west as the next step, what will the opponent do? What will the ghost do? Will the ghost come closer to me as a Pac-Man, or will the ghost go away? Are they random, or are they also, adversarial, or are they also smart? Are they after me? If I make a step, they're going to come after me and bust the game. What's going to happen? So what we're doing is at every single step, we're actually computing what to do, right? We're basically, we're computing from our behavior. So we're analyzing the behavior. So it is a little different from our previous algorithms. So, which is why I said that we are going to identify the behavior from the computation that we do. So there is going to be a little modification in the search algorithm, but then we're going to talk about the computation from behavior. From our own behavior, we're going to compute what's next, what's best to do next. All right. So here's a brief summary of what we're going to do for this lecture and the next. Okay. Today, we're going to talk about the scenarios where we believe that the opponents are smarter. Okay, I'll show a couple of examples where the opponents can be random. Okay, where there's uncertainty, and then we will cover that in more detail in the next section. But today we're going to talk from the algorithm's perspective. We're going to talk about the scenarios where the opponents are smarter. We believe that the opponents are smarter, and how can we design an optimal algorithm where we believe that the opponents are smart? What's next to do? So we're going to talk about basically deterministic and stochastic. Can anyone tell me the difference between these two? I've said these words quite a few times in these 4 weeks. And difference, do you guys know? What's a deterministic environment and what's a stochastic? Educated guess, meaning that there's uncertainty. The environment that you have is basically unknown. Like the next step that we're going to take, you're not sure how the environment, basically how the world reacts, okay, right? And deterministic is just like a Pac-Man maze. We know what the environment is, and then we can expand the entire tree, and we can just get to the bottom of the tree, and then calculate the value, right, and get all the way up at the root, okay. So as soon as we get the value at the root node, that means we know the solution, right? The solution, usually the values or the result or the goal is usually in the leaf nodes. And as soon as we can get to the leaf node, then that means we can propagate the value up in the tree, and we can get that value in the root node. And as soon as we get the value at the root node, we know the solution. We know the result of the game, right? So, as I said, just one more thing. Behavior from computation. Why we need to do that? Before, like in traveling Romania problem or simple Pac-Man scenarios, we were just devising a plan, right? So we were just like, just following a plan. Now here, at every step, we are thinking, right? We're thinking that what the opponents might do. We're thinking what the opponents might do, right? So we are, we're analyzing or assessing our behavior, which is why, if you remember, I said that do the goal formulation first before the problem formulation, right? So what happens is in real world scenarios, unlike simple Pac-Man scenarios, the world changes because there is uncertainty, right? As you say, just like I left for the class on Monday, and on the way, basically my entire plan changed because I wasn't sure that there will be a class or not. And then I was told that yes, there is a alert, and there are no classes. So as you move along in the real world, the problem changes. So does your solution. So your steps to take in the environment are actually according to the problem, and then your problem is dependent on the environment. How will the environment react, right? Which is why we have to compute the steps, and then we have to analyze or assess the behavior. So we're going to talk about a one-player scenario, one-player deterministic game, one-player stochastic game, and then we will add more players. Something like this. You see, we have just one pattern. What if we have two patterns? We can have two patterns, right? And we can say, okay, we have two Pac-Man now, and both the Pac-Man basically are trying to eat the dots as quickly as possible. And your job is to basically have another player, a friend of you, with you, and then you guys play together. There can be one player, two player, or even more players. And I'm going to talk about zero-sum games. Anyone, any idea what a zero-sum game is?
No one wins.
No one wins?
Yes. It's a game where one person's win becomes another person's loss.
where one person's win, one player's win is the other player's loss. Like checkers, like chess, like Go, like soccer, football. All these games where one party wins and the other party loses. That's zero sum. Okay, so, and then we're going to talk about perfect information. What a perfect information? Well, you can think of the maze as perfect information because when we apply DFS, BFS, and these algorithms, we actually have the entire tree expanded, and we know, where is what is the path, what is the solution, right? We have the least path solution. There's no uncertainty. But here, that's called perfect. Imperfect information is when you take a step and you're unsure of what the environment will do. Okay? You're unsure as a Pac-Man, you take a step, you're unsure of what the ghosts will do in response to that. That's imperfect information because you don't know. You have no information about how the environment will react. I give this example too for imperfect information. Suppose you design a robot to walk outside, to go from, let's say, from College of Education to Jack Rock Mall, right? Now, your design scenario would be that, okay, we're going to place the robot, it has a camera, it can, move some actuators, and then it will just walk and go to the Jack Rock Mall. Oh, perfect. That's perfect information. What if it is windy outside? What if your robot slips? You just, you don't know, you're uncertain. What if your robot is walking and all of a sudden wind blows it to the right, wind blows it to the left, or wind basically blows it to the back? It basically takes the robot away from its path, right? That's imperfect information because you don't know how the environment will react. So in those scenarios, instead of a plan, we have a strategy where we actually strategize at every single step of what we need to do based on what we observe from the environment. Okay, so in deterministic games, we'll start with deterministic games. All right, we basically need to formalize the entire problem. All right, according to how we just did in the past 3 weeks. We have to formalize. Basically, we have a set of states, right? We start at S0. S0 doesn't have, your root doesn't have to be just like your Pac-Man starting from one corner. It can be at any location. Your game can start at any position at any time. Okay, so your start state, your players, right? You can have one player, or you can have multiple players in the game. They all take turns. So remember, this is very, very important. Your players in tree search or graph search, when you will create the tree, they will have turns. Meaning, at one layer in the tree, at one layer, you as a Pac-Man will make a move, or you as as an individual standing in a right, you'll make a move, and then in the next layer, your opponents will have, or the environment will have their turn to play. So it will be multiple players making turns one after the other in a concurrent way, in an overlap. Okay, and we will talk about it. We'll see that very soon. Then there are actions, right? For Pac-Man, it's north, east, west, south, north, south, east, west, right? These are the actions, and they depend on players and the state and the kind of the game that you're playing. Okay, these 4 actions are specific, very specific to Pac-Man game. Then instead of a successor function, we have a transition function. All right, because we will see that now we're going to add terminal utilities at the leaf nodes where the game ends. We will have a value assigned to. Okay, so now we're not going to say, okay, here's the green node and that's the goal state because we have reached that state. It's not going to be like that. We're going to have utilities assigned to the leaf nodes. We will propagate them up in the tree, and then we will see basically which node has the highest utility as the maximum utility. Remember in week 1 and several times I said that we're going to design solutions, or we're going to design agents or software that are going to maximize their expected utility. So we need to find out the path that has the maximum utility for your agent, for your program, right? So far so good. All right, and then instead of a successive function where we were just taking actions, right? That is it. But now we're actually looking at the state too. Like we're at the current state, and if we are going to take an action, what will happen? So it's going to be a state and action pair instead of just action to be taken. Okay, we'll talk about that. And then basically in the form of uncertainty, we're going to have as policy or a strategy. Strategy and a policy basically is the same thing that I'm going to. Okay, so we're going to have our strategy to to basically take an action from the current state. So zero-sum games, as what Nathan just mentioned, that where one player's win is the other player's loss. Okay, so agents basically have opposite utilities, meaning if Nathan and I are playing chess, I'm going to be trying to maximize my utility by making moves that are best for me, at the same time minimizing Nathan's move, because I'm trying to beat him. I'm trying to win, and my win is Nathan's loss, and Nathan's win is my loss, right? So every time when I'm trying to maximize my utility, Nathan's utility basically is going to minimize. So that's what we call opposite utilities. Okay, the values. So if I'm getting the node or the action with the maximum value, that's going to be the minimum for him. All right. At the same time, Nathan will take the actions that will maximize his utility. At the same time, his maximum utility will be my minimum. So it's the opposite. Okay. So a single value that maximizes and the other minimizes, and basically those scenarios are pure or extreme competition, which is why we call them adversarial games. Okay, pure competition. And then there can be general games too, where you have multiple guys in your scenario. They're playing together, or soccer, football. There are two teams, but then there are like cooperating players, right? Players cooperating, and then the other team players that are opposing. Okay, so we're going to talk about zero-sum games. Here's a very brief table that I just have prepared, about some of the games that we have talked about and where do they fall in terms of deterministic or chance games or stochastic games, where there's uncertainty. Okay, and in terms of perfect information and imperfect. Okay, so I'm not going to go into too much detail, but we'll start with two agent or two player adversarial. Okay, where Alice and Bob basically, let's say, are playing together, right? Now we're going to talk about the example of a tic-tac-toe game. Have you guys played tic-tac-toe? Tic-tac-toe. Okay, so it's just like whichever player starts, they try to win, and the other player basically tries to draw them. All right. So what we do is, remember we said that we're going to analyze the behavior from computation. So what we do is we think about something like this. Alice sits before making the move. She said that if I put a cross in one position of tic-tac-toe, what is Bob going to do? Right? Because as opponents, I say if I make my basically pawn move, or if I move my knight, or if I move my bishop, what will Nathan do? Will he be able to kill that? Will he be able to just go further, make a further move? That is going to be like how harmful, how impactful it will be, right? So we're basically sitting and thinking and having a behavior from our computation, right? That's what we do in tic-tac-toe game. We say that okay, if I put a cross here, what is our next opponent? What is our opponent going to do? And this game can get much more complicated, even though there is nothing much going on. But now suppose that if I make this move, okay, and while I make this move, I'm going to think what Sophia might do, right? I can also think that if I make this move, I am thinking about what Sophia thinks that what I will do next. Then what I can also think of, if I make this move, I am now thinking about what Sophia thinks that I am thinking about what she will do. And this can grow longer and longer and longer, and it will get to a point where we will not even understand ourselves what the heck we are thinking about, right? It's just like, I think it was one of the episodes of Friends. I don't know how many of you have watched Friends, when Phoebe says, they don't know that we know that they know that we know. Something like that. She mentioned that. And then it was very confusing. It can get to really, really confusing because we're thinking, right? So let's think about single agent, something like this. Now, suppose that we have a Pacman agent, and the idea is to just look at how the tree looks like, okay? The idea is, if we take a step and do not eat anything, then we get a score of -1, okay? And if we eat a dot, we get a score of 10. Okay, simple. If the Pac-Man moves in the game, okay, in the maze, if it doesn't eat anything and makes a step, it's a score of -1. You're lowering your score. You're just randomly walking around in the maze by not making enough progress, right? But if you eat something, you will get a score. That's how we assign utilities. Remember, I said we are going to assign utilities or values to each of the nodes. And mostly the values are assigned to leaf nodes. So we do something like this, right? From this state, basically, we can construct an entire tree. We can say that Pac-Man can go either west or it can go east, right? It will get a score of -1 here and score of -1 here, right? Because in both steps, it just didn't eat anything. And then the next, it can either go further west, which is -1, -1. Oh boy. This is -2, right? This is also -2. This is also -2. What happens here? It took a step, right? Which is -2, but then it ate a dot. So our score is 8 here, right? Something like this. And we can then just construct an entire tree by going in like these scenarios. But this is just like very simple, just only 4 steps. Imagine the maze that we have. This can grow really large, right? The tree can grow large. Here, we have the value 8 because we know the game has ended here. So we assign the values to the nodes where the game ends. Yes. So that depends basically on how your opponent makes a move. So this is what I'm talking about here is just Pac-Man. And as soon as we get here, we stop because we have found the value, right? But in multiple games, in just a couple of slides, I'll show you how this basically tree will keep expanding because we have opponent nodes too, opponent players too. Okay, so stay with me in a few minutes, but as soon as you get here, you cannot expand further. That is it. You've just ended the game. So then after that, you're not going to expand the tree. Depending on what algorithm you're going to implement. If you're going to implement a depth first search, then it will expand all these branches, and then when it gets here, it will stop. But if it is a breadth first search, it will only expand that, and we will get here, and it will stop. Okay, because it finds the shallowest possible solution. But we'll talk about how this can get complicated in just a few minutes. So we get basically a score of 8, right? How can we assign a utility function here? Our utility function is going to be this. I have a current, my XY position, right? A simple utility function is that it is -1 if it takes a step, right? And it is +10 if it eats a dot. Our very simple utility function, where we just have basically 2 possibilities, right, at each node. If we take a step, we're going to assign a score of -1 to Pac-Man. And if the Pac-Man eats, we're going to assign a score of 10. And why we have like XY? Because you see here, we were at time t0. This is time step t1, right? Next step. Then this is the next step, t equals 2. And going all the way down at step n. And here, we basically assign the values. And then we will find the path that has the highest value, meaning maximum utility. Make sense? Now the actual fun part comes in the next few slides, where we will implement basically the minimax search algorithm. Okay, sounds good. So what we do is, what is the value of the state? Remember, the value of the state is actually the best achievable outcome, the best possible utility, best achievable outcome that you can have at your current state. Okay, please remember that. The value of basically the root is the value that you can get at its best in this entire game. So you get the values from the leaf nodes, and then you simply propagate them up, and then you find that out at the root. Okay. The node or the state where the game ends is called terminal state, because it is terminal. It terminates the game, right? Which is why it says terminal state, and there the value of the state is known. V of s is known. Okay, just simple terms. And then the non-terminal states are the ones where the value is not known. That is where the game doesn't end. And what minimax does is basically gets the maximum, expands the children, and then finds out which child node has the maximum possible value so that it can go in that path. Because we're going to find the path with the maximum expected utility, right? Make sense? Simple, all right? So the rules basically of the deterministic single agent game tree is basically, we again have rules. We have action effects. What happens if we take a certain action? Are we winning? Are we losing? Right? Each node stores a value, best outcome it can reach, and then maximal outcome of its children. This is what we're going to find. Okay? And usually leaf nodes have the utilities. Something like this here, you see? We say that here we win. We get the value. We get the maximum value. So in adversarial games. Now suppose in the previous slides, I mentioned that there was just a Pac-Man, right? And then there was a dot, right? And it was just like either it could go east or west, right? To eat the dot. Now suppose that we have ghost too. Suppose that we have a ghost, and remember we said that we can have more than one player, right? At one layer, it will be Pac-Man's turn, and then at the other layer, it will be Ghost's turn. Then how does the tree look like? You see here, from here we can say, from that blue state, the Pac-Man can go further west, or it can go east, right? We still have score of -1 here, right? And now, if we take this step, remember we said behavior from computation. What will our opponent do? These are the states that are not in our control anymore. As our agent, it's not in our control, because the next move is going to be the ghost move. Then we're going to think, if we take this step, what is our opponent going to do? So we let our opponent decide what is going to happen. So from the red part, the ghost basically can go west or it can go east, right? Here, ghost basically can go either west or east, right? Or further east. So these are the possible scenarios. So you see here, we say that when Pac-Man moves west, the ghost can either go west, one step west or one step east. If the Pac-Man can go east, ghost can still go either west or east, right? So that's how we create the tree. And then we simply expand, and then we get the values at terminal nodes or at the leaf nodes. Now these red states here, if we are thinking of adversarial game tree, these are the ones these are the states, or this is the layer that is not in our control. As Pac-Man agents, this is not in our control. This is basically the opponent's control. And in zero-sum game, what were we saying? Our maximum utility is our opponent's minimum utility, right? Minimize. So we can basically create a tree structure, something like this. To simplify it, we can do something like this, right? This, suppose that we have Pac-Man. This is our maximizing agent because this is us. We are trying to maximize our utility. And this is minimizing agent, right? Because the ghost basically is trying to minimize our utility. So we can do something like this. We can make it a little, formalize it a little bit. We say that the maximizing node is going to be denoted as facing up triangle in blue color or in any other color. And then after this, the facing down triangle is going to be our minimizing agent. And then after that, we have the maximizing agent again. And we can create a simple tree like this, right? Make sense? Super simple. Terminal state where the value is known. Exactly the same like how we talked about before. States under opponent control. Now, under opponent control is when we're going to find out the minimum, because our opponent is going to find a value that is going to be the least for us because they're trying to maximize their utilities, right? So when we are here, we're going to expect, as Pac-Man, we are going to expect that the ghost will try to find the value or choose an action that is going to be the most like opposing or dangerous for us. So we're going to expect, if we are smart, we're going to expect that the ghost is going to act smarter and going to choose the value that is going to be the minimum. Something like this. A ghost is going to basically, if we assume that the ghost is smarter, they're going to find the minimum value for us. So we should expect that minimum. Okay, that's why it's called minimax algorithm. All right, so something like this. And then for us, we're going to find the maximum. We're going to choose the maximum because we're going to find the value or choose the value that is the highest for us, right? So now you see here at each node, unlike the other algorithms, we are looking at the nodes or we are finding the path that has the maximum or minimum value, depending on at which layer you are. Correct? Make sense? Okay, let's talk about it. In a tic-tac-toe scenario, what happens? All right, for tic-tac-toe, we can assume very, very simple that there are only 3 values to the game. Like +1 when we win, -1 when we lose, 0 when it's a draw, right? Now, suppose that you create the entire tree, all right, you see like the the root basically is where the maximizing agent is. And then the further layer is the minimizing, then maximizing, minimizing, and all the way down to the leaf nodes, right? Maximizing agent chooses the cross to put. And minimizing agent uses the O, 0 or O to put in the tic-tac-toe scenario, right? Now, our job, basically, our goal is to find out the path, or basically, this value, propagate that up all the way in the root, and then at root, they say that the algorithm says that if we know this, then we already know that it's going to be a win for us. If it's going to be this scenario, right? Which is why having the value at the root node is basically the solution to the game. Now, if we expand all this tree, all right, and if Sophia comes to me and says that let's play tic-tac-toe game. If I already sit and as a computer, if I already expand this tree and already get the value, basically a value at the leaf node and propagate that up all the way at the root node where I currently am, even before starting the game, I can tell her, no thanks, I already know the solution. I already know the outcome is going to be a draw. Okay? So getting the value at the root node is actually the solution to your game. But now you see here, these are the only nodes that I just expanded. If you start expanding all this, even this small tree, 3 by 3, even this can get extremely large, really, really large. This brings us to the point where we're going to do alpha beta pruning. What are the ways we simply just identify? We just like that we really don't have to expand the entire tree. Okay. Look at this deterministic zero-sum game. Let's look at this. You see, facing up triangle, blue color, sky blue color is the maximizing agent, meaning it's going to pick the node that has the maximum value of its siblings. And then we have the minimizing agent that is going to pick the minimum value. What do you think the value will be here at this node? This node. What do you think the minimizing agent will pick from these two? So suppose that these are the leaf nodes. 2, obviously, right? How about this? 5. And what is the root value of the root node? Maximum. Five. Look at that. Exactly. This was my point. It's going to pick 5. So as a maximizing agent, I can sit and cry out loud for the entire day that I could have gotten the value of 8, which is better than 5. Why didn't I get this one? And minimizing, because we are being optimal. We're going to say, no matter how much I really want to get this value, my opposing agent is going to be smarter, and they're going to select 2 for us. So by thinking smarter, being optimal, this is still the best value that you can get. Even though your opponent may mess up here. It can mess up, right? Suppose you're playing, right? Playing one-on-one basketball with your player. Now you say that maybe at this step, maybe your opponent slips and falls, trips, right? Then you can get 8. But in extreme scenario, remember, pure extreme competition, you're going to assume that at every step, they're going to be your opponents. They're going to be smarter, which is why no matter how much you cry about the value 8, by being optimal, you're going to have the value 5. Make sense? 2, 5, and then 5. Oh, I already put that. Here's the pseudocode. If you understand these steps, better, I guarantee you that you can write minimax search algorithm within an hour. I'll send you a video tutorial of that to write the to write the code in Python, and that's going to be in your homework too. So we are actually running a little advanced in terms of the homework. So you see here, we will have the value, a function that's called def value. If your current state is the terminal state, then return. Then return the state's utility, the value, right, that you can get. But if your next agent is maximizing agent, then what do? Remember? Maximizing agent. No. Maximizing agent. What are we doing? From all the children, we're applying a max function. We're trying to find out, from all of these children nodes, no matter if they're 50, 100, or 1,000, find the node which has the maximum value. And for minimizing, we're going to find out the node that has the minimum value. So you see here in the algorithm, if the next agent is max, return maximum value. And if the next agent is min, return the minimum value. And you can just simply, once again, you can get these two functions, max value, min value, right? Your max value is going to be for each successor of the state. In your homework 1, what I mean is for each successor, you're going to say successors equal to problem.get successors, your current state. And when you write this line, basically in that variable, it just gives you all the children nodes. All the children nodes. So now that means you have multiple nodes. It's an array, right? It's a list of nodes with XY position, which is why I say that for each successor, well, when you say get successors, for each successor in the successors, find out the maximum value. You just run a maximum function. That is it on the children. And it's a recursive algorithm. You recursively apply that, you recursively expand the entire tree, get all the way down, and keep finding the maximum value. And you know why v is minus infinity here and plus infinity in the min function? Does it make sense? Because we're going to be optimal. We're going to be smarter to say that we're going to start, basically, we're going to start with the situation where we say everything from this step forward, whatever we are going to think of is going to be better than what we are currently thinking. It's a lower bound. It's a lower bound, which is why you put minus infinity here, and this is the upper bound. Okay? All right. Even closer, even further closer to your code, your homework 2 code, here, you see, if the terminal test. What do I mean by terminal test? When I say if problem dot, one second. If problem dot is goal state and my current state, xy, then return the path. Otherwise, insert the next node in the path. Run it.
It says homework 2. It's on homework 1.
Yes. Homework 2 will be in the coming weeks.
Oh, so this will be.
Right. That's why I said we are actually running in a little in advance in terms of the homework. So this is the max value function. You see v minus infinity. In Python, you're going to initialize v as minus infinity as this. And then plus infinity in your min function. Come on. It's frozen. V equals, if you write this line in Python, it will initialize v as minus infinity or plus infinity. Okay? Sounds good. So please keep that slide in mind. All right, a minimax example. Now, this is going to be very, very similar to one of the algorithms that we have already talked about. So I'm going to ask this question after I expand this tree, and I'm going to ask you, which algorithm does it look very similar to? Just pay very close attention, okay? Now you see here, so this is the maximizing agent that we are at, right? We're going to expand A1, then we are going to expand A11, A12, A13, then A2, A21, A22, A23, A3, A31, A32, and A33. Which algorithm does it look very similar to you? Depth first search. Leftmost solution. What is this time complexity? If b is the branching factor and m is the maximum depth. B to the power m. It's exponential. It's exponential. So here you see, this is the minimizing agent, right? We're going to assume that the minimizing agent is going to select 3 for us, right? From these. Here, we're going to assume that the minimizing agent is going to select or choose 2 for us because we are implementing a min value function here, right? And then here it's 2, right? It's actually an exhaustive DFS algorithm. It's an exhaustive, it goes in all directions. All right, which is why its time complexity is b to the power m, but space is still b times m. Space is still linear. It's complete only if the tree is finite. For a chess game that has a b35 and about 100, that solution is going to be completely infeasible. That means the only minimax search algorithm is not going to be feasible for you when the tree grows really, really large. Okay. Once again, here you see here it's just going to simply select 10 for us. Okay. Here it's going to simply select 9 for us because this is the minimizing agent. No matter how much we really want 100, it's going to be, because if we are optimal, then it's going to have the value 10 for us in the maximum value. So now you see here, b to the b35 and 35 to the power 100. That's going to be an unbelievably large number. Modern computers will not be able to solve it. So the question is, do we really need to explore every path? If we are playing optimal, what we can do is, at whichever layer we are, we can think of who is our opponent or who's the other player at the top layer. We can basically cut down or shorten the search quite a lot. Because if I'm the maximizing agent, and if I'm trying to find the maximum from the lower layer, but I'm going to say, if I keep looking for the maximum value, the minimizing agent is not going to care about it, because the minimizing agent will only care about the minimum possible value. So why am I searching for the entire tree? It's not going to be feasible. We'll see. We'll talk about it in just a few moments. Okay. This minimax search is only optimal if we are playing against a perfect player. Otherwise, no. Okay, something like this. Look, suppose. Oh, okay. I'm going to skip that a little bit because I had a tic-tac-toe scenario in which we said that suppose that our player is smart, then what happens? Then we are optimal. If the player is not smart, if the opponent is not smart, then this algorithm is not optimal. Now, look, once again, Ronald's question. What if the, how am I going to go to, okay, let's see. I don't know if it's playing. So suppose that you have two goals, and remember, the more steps you take in the game, the lower the score. What do you think is the best solution in here? If your players are basically, if the opponents are moving randomly. Go down, but what if your goals are after you? Then the best way is, you see, if this guy comes up, then you're stuck. The best way is to end the game in the least possible, not the least possible, highest possible score. Simply hit the yellow-orange ghost and bust the game, right? Because our goal is to maximize our score. So if we keep moving around randomly, we're going to keep having -1, -1, -1, -1, right? We're going to try to avoid that. So what we're going to do is, how can I play it from here? Play. Okay. Let me play it for you and then see, what's the best way. You see here? So if our ghosts basically are random, it's gonna sit and think that, oh, if I move here, this guy comes up, I'm gonna move here. If this guy comes closer, I'm gonna move like a few steps here and there, minimize my score, go minus, and then the game will end. Why don't I just simply quickly run to this orange ghost, and that is it? Just like this. What happened? Oh, nope. This. You see here, yeah, wrong one. So simply hit the ghost and end the game. That's it. But look at the ghost's eyes. Don't they look too cute? Don't you think that they are not like adversarial? They're not after you. They don't have swords with them. They look really innocent, right? What if the ghosts are random? Meaning at every step, when we say is random, it's just like every time you take a step and you roll a dice or you toss a coin. What am I going to do? It's random. I don't know. So if we assume that the ghosts are random, okay, then we're assuming that at every step, these ghosts are simply just rolling a dice and deciding what to do based on rolling a dice. They're not after you. They're not killing you. They're just like babies with big eyes, right? So you say that eventually, if I play many games, there will be a time there will be a time that this blue ghost might actually go this way. Might actually go this way. Then after several scenarios, you sit and you think that, you know what, a best move might be to take west. You see that? So we have to think about what the game is, either it is with the random ghosts or it is with the smart players, smart opponents. You have to think what the scenario is. And Minimax algorithm basically is optimal when you assume that your opponents are smart, are smarter, right? Okay. Okay, yeah, in realistic games, we cannot search. Remember, if our tree is way too large, remember we said that depth first search has the exponential time complexity, and breadth first search had, it was finding the shallowest solution, right? And we combined the benefits of both, and we came up with a similar solution, and that algorithm was called before ASR. We said that we combined, remember iterative deepening? Remember iterative deepening? We said that let's set the depth limit to only 1, apply DFS. Then if you don't find the goal, then increase the limit to 2, then apply DFS. If you don't find the goal, increase the depth limit to 3, and we were iteratively deepening. Iteratively, because if the tree is too large. We're not talking about uniform class, we're not talking about ASR search, we're talking about the exhaustive DFS, which is Minimax. So we talked about this algorithm, right? Iterative deepening. But if we don't go to the leaf nodes where the actual values are, where are we going to go bring those values from? Because we're not even getting to the leaf nodes. How are we going to bring those values? Where? That takes us to the point of evaluation functions. Those are the expected values or estimated values. Estimated values, not the real values, because the deeper you go in the tree, the better the solution, because you're exploring more, right? But if we are applying iterative deepening for larger problems that have larger trees, then we will have to basically estimate the evaluation function. And we'll talk about the estimation function or evaluation function right here. Suppose, once again, Nathan and I are playing, and I'm, in black, Nathan is a, white player. So suppose that we have this situation. How can we solve that using Minimax search algorithm? Because this can grow really, really large, right? For chess is 35 raised to the power 100. How can we basically solve that problem using iterative deepening? So what we can do is we can get to the evaluation function at depth 3 or depth 4. We can think of the next 4 moves, right, by the opponent, and we can estimate what our opponent might do. We can only estimate it. How will that estimation be arrived? How will we arrive at those estimations? Typically, the experts write the evaluation functions. And in a chess, it can be a weighted linear sum of your moves. Weighted linear sum, like Fn of s, F2 of s, F1 of s. And you know what these are? F1 of s, F2 of s, F2, Fn of s. These are actually, it is like, where is your knight at? Where is your bishop at? How close your queen from the wall? How close is it to call a checkmate? So these are all those possibilities, okay, you think of at the current state, and then you just do estimate basically, or you calculate the linear weighted sum of all those possibilities that you have. Now you might be thinking, where are these W's coming from? Where are these weights coming from? How do we, I'm calling it a weighted linear sum. So I'm saying that I'm giving this more weight than this, because W1 might be lower than W2. How will we calculate that? That actually typically happens, 5 minutes left. Typically happens, basically, you let the computer or the software play so many games, find out the situations, what happened, take the data and apply a sophisticated machine learning algorithm and get those waves, such as neural networks, support vector machines, Bayesian networks, things like that. Okay, you calculate. So we'll talk about like what a bad evaluation function is, but the more important thing is alpha beta pruning. How can we cut? Like, how can we decide upon which branch to not even explore anymore? Now look here, that example again. Let's look at the example. Come on. All right. We talked about this example, right? Now pay very close attention because this is very important. Okay. Wake up. Just 5 more minutes, please. Now you see here, we said that we're going to propagate the values upright at the root. While propagating the values, we can put a very simple check in our code that is going to help us cut the tree search to almost half. Let's talk about it. See here, at this stage, the minimizing agent is going to choose a minimum value for us, right? We go to the next node, okay? We go to the next minimizing node. We get the value of 2, right? We get the value of 2. Now, as soon as the minimizing agent says that I've gotten the value of 2, since my previous value is greater than my current value, right? I'm going to sit and think, my top node, the node above me, is the maximizing agent. If I select 2, will it think that the maximizing agent will ever care for that value? No. The minimizing agent is going to say, oh, I've got 2 here, but there's a better value right here. And the maximizing agent will never care about this anymore. It will never care because it will always go for 3. It will stop there. What it will do is, well, it's not going to care for this anymore. So imagine if it had like 50 more layers below it. We have cut that entire tree, cut that entire branch, and we stopped. Now let's suppose if it goes this way, right? And it finds 14, okay, this is good. This is good because this is greater than 3, right? As soon as it gets here, finds the value 2, well, we don't explore that. Now you say here, if this is the value it has gotten, basically the maximizing agent is not going to care for this anymore at all, right? So in iterations, it will first cut these and then it will cut this. In iterations, it will cut this and then it will cut this. See how much we have cut? Like how efficient we have gotten, just thinking what our opponent is going to think, right? Because our maximizing agent is only caring about the value 3. So the code basically is going to be like this. So the actual pruned tree is going to be like this, right? Here, all what you have to do is everything the same. You get the value V max. If V is basically greater than beta, then return V. That's it. Just stop there. Because our value, our current value, the previous value, is actually greater than the minimum, the one that we chose next. If it is greater than or equal to that, then stop it. Just return. That's how we just prune the entire tree. And on the other side, this is why it's called alpha beta pruning. Okay, beta is for the minimum and alpha is for the maximum. And you simply pass those alpha beta at every recursive step. That is it. Okay, now you see here, this example. Look at this. Look at this number n. Let me try to explain how helpful it is. Look at this number n. Which node do you think is going to care the most about this value? And suppose that there is another minimum number in here. Which node is going to care the most about this value? The one above it, right? The one above it. Now, if I propagate n all the way up here, and then make a comparison, if alpha is greater than, if a is greater than or equal to n, right? If a is greater than or equal to n, then I really don't need this. I really don't need this. In steps, simply cut this entire tree. So this condition is very important. And for minimizing agent, suppose that if there was a b value, and if it is less than or equal to, then just simply stop. This way you have pruned. Let me just go over one quiz quickly. So in alpha beta pruning, basically we're doing the meta reasoning. Okay, I'll explain that some of the. What do you think is the minimum value there, up there? Here, 8, right? As soon as we get 4 here, let's make a check. Remember? So this is our value. V1, V2. We said V1 is greater than or equal to this beta value. It is greater than or equal to beta value. Stop. Stop there. That is it. Don't explore F. And then after this step, when you go to the maximum, there is really no need to prune this. So you can prune F and D and cut it into half, right? Look, the tree has cut into half. Another quiz. Look at this. Now suppose, now let's be a little tricky. What is going to be the value here in this diamond? 10, right? 10, come on. How about this? 100? Should we explore 8? No, right? Because the maximizing agent is saying that if I select 100, this guy is never going to care about this value 100. It will always choose 10 minimum for me. So it will first prune G, and then it will prune E. So we have cut this entire branch. How about here? 2. So we have 10 here, right? We have 2, and then we have 20. Should we still keep going? No, right? So this is 20. So this doesn't get expanded anymore, and this doesn't get expanded anymore. And now if we have 2 here, what's going to happen? Look at the condition. 10 is greater than or equal to 2, right? Cut this, and finally cut H. So G, E, then N, L, and H. Huh? Sorry, not this one. Okay, this way. G, E, L, and then H. Prune them, cut them completely. So this way, its complexity can get up to half. B to the power m divided by 2. That's how you can solve problems for larger trees using alpha beta pruning, by simply put those 2 small checks. If V is greater than or equal to beta, which is the minimum value, right? Then return V, then stop it. Or if alpha is less than or equal to, if V is less than or equal to alpha, then stop for minimizing agent. Make sense?
The red is the maximizing agent?
No, the triangle facing down is the minimizing agent. The triangle that is facing up is the maximizing agent, because we are just like, facing it up, meaning maximum. It's just a notation to better understand. Any question? We're 5 minutes over. I was a little fast because we're already behind the schedule.
agent?